Having discussed the actual z-score itself, and that equation is useful for just making direct comparisons between individuals, we're now going to start talking about actual inferential statistics. And again, when we talk about the term inferential, we're inferring from a sample to a population. So when we're talking inferential statistics, we're generally talking about we have a sample. We have multiple people who we have scores for, either individually or group scores. And typically we have an independent variable and a dependent variable at a minimum. They can be much more complex than this. And when we're looking for the pattern in events, we're looking for a mathematical pattern through statistics. So our most simple type of inferential statistic is called the single sample research. And what this means is that we are using an inferential statistic used to infer the results based on a sample to a population. And the population, the sample that we have, we actually do not have differences. In other words, what we're comparing is there a difference in our sample with the population? That's what it means by single sample research. In other words, our IV this is quasi-experimental in that we actually have not measured two different groups or three different groups or multiple groups. We've measured a single group. We have one DV, but we have a pre-existing DV from the population. And our question that we're trying to infer is, do we find a difference with our sample from that population? And this is going to naturally develop from that z-score statistic we already talked about. So we're talking now about the idea of statistical significance, determining by comparing an obtained test statistic to a test statistic probability distribution. In other words, whenever we're actually talking about an inferential test, one of the things that we're adding to the equation is the statistical significance of the test. In other words, is it actually statistically significant? And we've talked about this already within correlations and regressions, but we really need to kind of zero down a little bit more of how this actually works. So let's just talk about terminology. The obtained test statistic is the statistic calculated using the sample data. So anything that we calculate, whether it's an R, whether it's a Z, whether it's a T, whether it's a F, those are various different statistical tests. However, the value we get at the end is the obtained test statistic. We're going to compare that obtained test statistic, whether it is a hand calculation and a chart, or whether it is a computer program that's doing it for us, to a test statistic probability distribution. And basically, this is a graph, if you will, indicating the probability of obtaining a particular value of the test statistic. In other words, if we actually calculate an R, a correlation, and we get a value of positive 0.67. The question then becomes, does that obtained test statistic of 0.67 actually meet the required bar that it would be so unlikely in the test statistic probability distribution, assuming there is no effect, that we would be unlikely to find it? In fact, the social sciences have chosen this to be a 5% bar. So in other words, we're asking, does our obtained test statistic fall in the test statistic probability distribution based on the sample size, to where that result would be unlikely to occur by chance at a 5% or lower level. So the critical test statistic is the value that test statistic needs to indicate a significance, effect, or relationship. So again, we've got these terms. We're obtaining a test statistic from our sample. We're comparing it to a distribution of possible scores based on the size of the sample. And then based on that, we're looking to see, does our obtained test statistic equal or exceed the critical test statistic for the probability that we're indicating? So again, statistical significance is simply a measure of probability. How likely is it that we're right, and how likely is it that we're wrong when we're saying we found a difference, a pattern, or an effect? So a part of that also then becomes a question of, where are we looking for this difference? So for example, if we're looking for a test distribution, so again, this is the actual values, not of our particular score, but our test distribution values. So we're basically wanting to look at saying that 95% of values would make us reject our hypothesis. Basically, we are not certain that there's an effect. And if we're in that 5% of values, or higher, we would say that we have statistical significance. Now, if we actually have a directional hypothesis, for example, I expect there to be an increase in one group over the other. That is a one-tailed test. Our alpha is 0.05, and when I look at the test statistic, I'm only needing to see that increase. I'm looking at the top of the tail, that 5%. It's why it's called a one-tailed test. We're only looking at one tail of the distribution, the positive one, that increase in this case. It could also be a negative one. I could also have a directional hypothesis where I expect one value to be lower than the other. This would be still a one-tailed test. So our critical value is going to be based on comparing our obtained test statistic to this estimate of values based on the sample size. So if I have a score that's below that 5%, that critical value, I do not reject the null hypothesis. I basically say there was no relationship. The null hypothesis that there wasn't anything occurring was correct. However, if I'm above that critical value, I claim that I'm rejecting the null hypothesis. There is an effect. There is a statistically significant effect, which again just means the probability is very high that I'm correct when I say that I found this pattern. If it's a two-tailed test, in other words, we don't have a directional hypothesis. I just believe there's going to be a difference. This is actually a less powerful test because I now have to split that 5% by both the positive and negative tail, and that's why we call it a two-tailed test. We're now looking at a smaller set of values, either positive or negative, because our p-value of 5% is still 5%. So in this case, our critical value of plus is only 2.5% of all the top possible values, and our critical value negative is only 2.5 to make up that 5%, so our alpha is the same. Our rejecting the null hypothesis stays 95%. So this is just a mathematical reason and a methodological reason why it is a good idea to actually have directional hypotheses if, and this is a big if, the theory and past research indicates the likelihood of that. So if you're researching something that there is no previous studies about, you're probably going to have a non-directional hypothesis. I'm expecting there to be an effect of some kind. I really don't know if it's going to be positive or negative. That is a two-tailed test. But generally, one of the reasons we do the lit review and we look to see what's already been found is to help us create a directional hypothesis because it's going to be more likely that we find that effect. In fact, it's going to be twice as likely as we're only looking at either a positive or negative end of the tail. So single sample research, we compare a sample. In other words, we have measured a group to a population. That means that we have to know what the population is. So we're comparing the sample mean to a sample distributions mean. The sample mean is the mean of the specific sample. The sampling distribution is an estimate of the population's mean by this exterior source. So this is kind of, again, a little bit of a blending of the experimental method and inferential statistics with kind of more non-experimental archival research. For example, I am finding what is the mean population score on, for example, income for the entire United States based on the US Census. That's published information. I can get that mean. How does it compare to the mean sample of 50 people that I've measured that live in a low income area of Kansas, the state of Kansas? That would be an example of single sample research. So again, we're looking at the sampling distribution and we're asking when we compare our critical value of the mean of our sample to the overall mean, is that difference large enough that we would expect to only find it due to chance less than 5% of the time? So again, just a reminder, statistical significance is not a solid number, it's an estimate, and it's an estimate of probability, and it's simply the probability of whether we think we're right or wrong. So when we're looking at this, we often use terms such as standard error of the mean, and this generally represents the idea that when we actually have a mean, especially of a sample, it's an estimate of where it is. In other words, there is some error, and we want to account for that as well in our statistical calculations. So how do we actually calculate a z-score? Is the sample mean different from a population mean? So this basically is, again, a fairly simple equation. We take the mean of our sample minus the population's mean divided by sigma mean. And sigma mean is simply the actual standard deviation of the population divided by the n of our sample. So again, we'll walk through this a little bit better, and we'll have a few samples where we actually put numbers to this. But basically, the values that we need to run this test is we need to know our own mean, and we need to know the size of the sample that we took. We also need to know the population's mean and the population's standard deviation. So how many standard deviation units is the sample mean from the population mean? That's what we're calculating. And for this test, we always have the same critical value because the actual sample size has already been adjusted in. So there isn't an actual chart on this. There's a straight value. For a one-tailed test, we want to see an obtained z-score of positive or negative 1.645 or higher. That represents that we are within that 5 percentile. And likewise, if we have a two-tailed test, we need to see a positive or negative z-score of 1.96 or higher. This is one of the reasons the z-test is a relatively simple test. We don't actually have charts. We don't have to calculate what the actual sample size is because it's already been adjusted for us, and we already have those values that we can simply look at. So where in almost every other case, our critical value is going to be different depending on our sample size, with the z-test for single samples, all of that's already been done for us. So we always have the same critical value. If we have a one-tailed directional test, we're looking for a value of plus or minus 1.645 or higher. If we have a two-tailed test, in other words, we didn't know what we were looking for, we just expected to find a difference, we need a positive or negative 1.960 or higher. So the assumptions of the z-test, we have a known population mean, and we also have the standard deviation for that population. And notice that when we're talking about a sample mean and standard deviation, we use x with a line over it, and we use SD or S. However, when we're referring to a population's mean, we refer to it as the Greek letter mu, and we represent the standard deviation with sigma. So sample mean is the next thing we need. We need a sample mean using interval or ratio data from our sample. Finally, we need a normal distribution, and we need a sample size of 30 plus. That is one of the assumptions of the z-test that I really want to point forward, is that you cannot use this equation if you have a sample of less than 30 people. There has to be 30 or 30 plus to be able to run this z-test. So that's our first actual inferential test. We have a sample, we've calculated the mean, we know the n, and it's over 30. And we're comparing it to a population mean and standard deviation that we already have value to. We run the equation, we get the obtained test statistic, and then we just compare it to that critical value, whether it's a one-tailed or two-tailed test.